Good morning, class, and welcome to this lesson on normal force. Today we are going to be able to determine the normal force of an object under a variety of conditions. It's actually going to be about 5 different conditions. So this video is going to be a little bit longer, but it's going to be very, very important. I'm going to try to do it all in one so that way you have it all referenced. I also suggest maybe you want to highlight this or write down a note somewhere. I'm going to go over some very, very key concepts right now, so you might need to watch this once. You might need to watch this again a few more times later down the road as we solve more difficult problems. So let's look at our first condition. Our first condition would just be an object at rest on a horizontal surface. So let's just pretend I have an object sitting on a horizontal surface. If I draw a free body diagram, and a free body diagram is the most important key here, gravity is pulling it down, mg, and normal force is pushing it up, okay, n. Because this object is not moving, because its acceleration is equal to 0, the normal force equals the gravitational force. And let me show you why. Right now, normal force is going up in a positive direction. Mg is going down in a negative direction. So if we drew our equation out, F net equals ma, I highly recommend drawing F net each time. Our net force is going to be, looking at this diagram, it's going to be the positive direction and the negative direction. So F net equals normal force minus mg equals ma. N is positive because it's pointing in the positive directions. I put minus here for mg because mg is going in the negative direction. So acceleration is 0. So n minus mg equals m times 0. So n minus mg equals 0, or n equals mg. So let's pretend for a second this is an 80 kilogram object. N would be equal to 80 kilograms times 10 meters per second squared for gravity. So normal force is equal to 800 newtons. So notice what I did there. I wrote my equation out first. F net equals ma. Remember, key part of the AP test is writing the equation first. I have my forces. These two are equal and opposite. Equal and opposite. So n minus mg equals ma. That's where I get the F net from. These are the two forces I'm looking at. N minus mg equals 0 because acceleration is 0. N equals mg. Now you might be thinking, why not just say, okay, n's going up, normal force is going up, mg is going down. Third law, equal and opposite, n equals mg. And you would be absolutely right. This is where we got to this point eventually. We did. They're the same. And so you might be thinking, I can just do that right off the bat, and that's true. But the reality here is I'm trying to give you problem-solving skills for that way when it's not an easy situation. Right now, an object at rest, acceleration equals 0. That's a very simple situation. But I can almost guarantee that's not going to be the situation you're presented with as we get more and more complicated, and you're not going to get that kind of easy thing on the AP test. So let's look at a second situation. Actually, this is going to be 2 and 3. Take, for example, someone is on an elevator. And these are actually called elevator problems. These are called elevator problems. Let's say someone is on an elevator and they are standing on a scale. The reason we say standing on a scale, because a scale really is a measure of the normal force. A scale really is a measure of the normal force. When I stand on a scale, I weigh 185 pounds. So the force of gravity is 185 pounds pulling me down, and the scale is pushing back up with 185 pounds, and then the dial reads 185. So that's what a scale really is, a measure of normal force. So let's say this person's on a scale, and they're going on a typical journey from the bottom floor to the top floor. Okay? During the very first part of that journey, it is the elevator accelerates to get up to speed. Then it has constant velocity, and then it decelerates at the very top to slow down, or accelerates in the negative direction. So we're actually going to look at all 3 of these situations right now. So the first situation, it's accelerating positively. Let's say this elevator is accelerating at 2 meters per second squared. 2 meters per second squared. This is actually very fast. This is very, very fast. But I'm trying to make it simple math by using the number 2. Okay? So let's go back to our free body diagram. This person is standing on the elevator. So gravity is pulling him down. Normal force is pushing him up. Nothing has changed there. Nothing has changed there. So we get N minus mg equals ma. I'm sorry, I should write this out again. F net equals ma. The net force is N and mg. And now it is accelerating. The elevator is accelerating, so we can't cross this out anymore. A equals 2. So we have normal force minus mg equals m times 2 meters per second squared. So if I want to now solve for n equals m times 2 meters per second squared plus mg. And let's just say again this person is 80 kilograms. So n equals 80 kilograms times 2 meters per second squared plus 80 kilograms times 10 meters per second squared. So we get 160 newtons plus 800 newtons for a total of 960 newtons. So notice, look back at this problem here. I had an 80 kilogram object. Now I'm talking about an 80 kilogram person. They're the same thing. An object at rest, normal force on a horizontal surface is 800 newtons. But when it's accelerating upward, the normal force increased. And that's why you have that funny feeling when you're on an elevator and it first starts out, you feel the acceleration of the elevator going up. And that's why your legs sometimes feel a little bit heavy. Because for those first few seconds, your body's actually supporting more weight. Okay? There's more of a force on your legs. So in this situation, that's a 160 Newton difference, or 16 kilograms, which is about a 32-pound difference. So this person on the scale, who should be 80 kilograms, this scale would read 96 kilograms on that scale. Or if this person was 185, this scale would read 215. It's approximately. So this person is on a horizontal surface. So once again, this is situation 2. Horizontal surface, and it's accelerating upward. Okay? Accelerating upward. Let's go to situation 3. The second part of the trip. The second part of the trip where it's at constant velocity. Constant velocity for the second part of the trip in the elevator. And the reality here is I'm not going to work the whole thing out. Because it's at constant velocity, acceleration equals 0. So even though it is moving, it's still not accelerating. So basically we have the same exact equation. F net equals ma and a equals 0. Oh, I'm writing it again. So n minus mg equals 0, and so we would have n equals mg. So I'm not going to write all the numbers out again. So at constant velocity, acceleration is still 0. So you need to be very careful with that in word problems. If it's ever talking about constant velocity, we can automatically make F net equal to 0. Okay, that's a very, very key part there. Don't confuse motion with acceleration. Just because it's moving doesn't mean it's accelerating. Okay? Situation 4. This is the horizontal surface, and it's decelerating, or a more accurate term would be negative acceleration. So this thing is decelerating now. So we're going to start off the same way. Normal force, mg. Free body diagram. F net equals 0. F net equals ma. Our net force is going to be n minus mg. These are equal and opposite. So n positive, mg negative. N minus mg equals ma. Now let's say again it's going to decelerate at negative 2 meters per second squared. So notice this is now negative. This is now negative acceleration. And there's something else I want to point out too. This elevator is still going up. The elevator is still going up. The issue is it is slowing down going up. So acceleration is still negative 2 meters per second squared. So right now, N equals ma plus mg. Okay? N equals m times negative a plus mg. So let's plug all our numbers in. N equals 80 kilograms times negative 2 plus 80 kilograms times 10 meters per second squared. So we're going to have our 800 newtons again, but now we're going to subtract 160 newtons for a total of 640 newtons. So once again, if it's decelerating, then we're actually the scale would be less. So the normal force would be less. So you can see here from these four situations already, normal force depends on the frame of reference. In a typical frame of reference, it's just equal to mg. Simple. N equals mg. Done. But if it's accelerating, we have to expand it out a little bit and see which direction it's accelerating. And depending on that direction of acceleration, it will determine if it's going to be up, if it's going to go less normal force, or more normal force. Okay? So I plan on doing one more, situation 5, on an incline or at an angle. But I'm already 12 minutes into this video approximately, and I think it'll be better to explain this on a different video altogether, because it is also a little bit more, it is a little bit different. So work with that, and now please go to my next video, normal force on an incline. Okay, normal force on an incline. Thank you.